whenever you'd like.
Awesome. All right, can everyone hear me? Cool. Can everyone see my slides? Excellent. Hello, everyone. Thank you for coming to WNB.RB's October meetup. My name is Emily Samp. I am a senior developer at Shopify, as well as one of the co-founders of WNB.RB. So today I'm going to talk to you about a project my team is working on at Shopify. And the goal of this project is to replace Sorbet's parser with Prism. Now, most Ruby and Rails developers probably won't encounter these terms very often. And because of that, you might be thinking this talk isn't for you, or that you won't understand it, or maybe even that you want some ice cream. No judgment. I think about ice cream all the time. But I assure you this talk is for you, because at the end of the day, what I'm actually going to be talking about is this. I'm going to be talking about making a big change in a complex system. As a software developer, I'm sure you can relate to this scenario. You're asked to work on a legacy application. It's big, hundreds of thousands of lines of code big. It's written in a language you don't know super well, and now you have to make a significant architectural change. How do you do it? What kinds of things will you learn along the way? That's what we're going to be diving into today. During this talk, I'll explain everything you need to understand the technical details, so don't worry too much about being left behind. By the end of our time together, I'll summarize some important learnings that you can take back to your own work, even if you still think sorbet is just a type of ice cream. To kick off this talk, we're going to start at the very beginning to understand what this project is and why it even needed to happen in the first place. I'm calling this chapter Ruby's parsing problem. So at Shopify, I work on the Ruby developer experience team. Our goal is to improve the experience of developing Ruby applications with tools like Sorbet. Sorbet is a gradual type checker for Ruby. It was developed at Stripe, and we've been using it at Shopify since 2019. Now, what do I mean when I say Sorbet is a type checker? A type checker is a piece of software that can statically check, and that means before we even run our code, whether or not it follows the rules of the language it's written in, and flag any errors to the user. So let's see how this works in practice. So let's say we wanted to write a method called sayHello. This method takes one parameter, a name, and then returns the string hello concatenated with the name and an exclamation point. The first thing we can do in Sorbet is add a signature, which tells Sorbet that the name param is going to be a string and that the method will return a string. Now, when we call that method and pass in a string, obviously it'll work as expected. However, what happens if we try to call this method and pass in an argument that's not a string? Well, in this tiny example, it's obvious that it'll raise an exception within the method because we're trying to concatenate a number with a string, which in Ruby raises an exception. However, in a large application, this is the kind of error that could easily be missed until we run our tests in CI, or we see the error in our production monitoring. But that's not the case if we're using Sorbet. Sorbet is going to raise a type checking error, telling us that it expected a string for the argument, but was instead given an integer, allowing us to fix this issue before pushing to CI or seeing the error on production. But how does Sorbet do this? How does it know before we even run our code that we've passed the wrong kind of argument into this method? To do that, it has to use something called a parser. A parser is a piece of software that analyzes code and then converts it into a structure that a computer can understand. It is literally code that helps us understand other code. How cool is that? So let's see what this looks like in practice. If we revisit our sayHello example from before and look at how Sorbet would parse it, the parser will take each part of the code and restructure it into a format called a parse tree. This is what the parse tree would look like for our sayHello method. The call to the method itself would be stored in one object called a node, which is right here. This type of node is called a send, and that's just the name for nodes that refer to a method call. And then the argument to this method is an integer with the value 5, And that would be stored in a different node that is referenced by our send node. Now, this is obviously a very simple example. When you parse an entire program, you're going to end up with a parse tree that looks more like this, or infinitely more complicated. Representing the code in this format allows the computer to understand and manipulate its structure, to gain information about how all the parts of the code relate to each other, and thus tell us things like, this method was expecting a string, but it got an integer instead. Now, Sorbet is not the only piece of software that needs to parse Ruby code. Other developer tools like Rubocop use the parser to analyze code and find linting and style violations. The Ruby interpreter also has a parser built in, which allows it to read and run the Ruby code we write. And let's not forget that there are other implementations of Ruby, like JRuby, which also need to parse Ruby code. And on and on and on. Now, if you're looking at this slide, you might make an assumption. You might assume that all of these tools and Ruby implementations use the same parser to parse Ruby. And that would be a very reasonable assumption. Unfortunately, until recently, it would have also been very wrong. In fact, I can name at least 7 Ruby parsers between different Ruby implementations that each had their own parser, and community parsers such as Seattle RB's ParseGem and the White Fork parser, and even the Sorbet parser. Now, to be clear, there is nothing wrong with any of these parsers. They are all perfectly functional. The problem exists more at a community level. The fact is that none of these parsers was ever meant to be shared between projects. That means that every time the syntax of the Ruby language changes, at least 7 teams need to get together and implement that change in one of the parsers. It means that in each of the parsers, we're introducing different subtle bugs that are just waiting to be found by unsuspecting developers. So this is where my team and I were, helping to maintain the Sorbet parser and keep it up to date with modern Ruby syntax. It was a lot of work, and it slowed us down. That is, until recently. Enter Prism. Prism is a new Ruby parser that was developed at Shopify. It was shipped as an optional parser in CRuby 3.3, and it will potentially become the default parser in CRuby 3.4, which is set to release this Christmas. So when the folks at Shopify set up to build Prism, they had 4 goals in mind. The first was to make it error tolerant. That means that the parser shouldn't just stop parsing as soon as it encountered a syntax error. It should parse as much of the program as possible, no matter what. The next was to make Prism maintainable with readable documentation and good test coverage. They wanted to make it fast and efficient, which I think is pretty self-explanatory. And finally, they wanted to make it portable, meaning it could be used in a variety of other projects. And in my opinion, this is the most groundbreaking of all the principles. In a language with at least 7 existing parsers, the Prism team wanted to create a parser that could be used across projects, reducing the toil in our community in order to keep tools up to date. And so my team thought, what if we replaced Sorbet's existing parser with Prism? What if we did a lot of work now to help us avoid even more work later? What if we'd made Sorbet easier to maintain and perhaps even more performant in the process? And so we agreed, and it was time to actually do the work. Now, earlier, I explained that Sorbet parses Ruby code in order to convert it into a format that is easy to type check. Of course, that was an oversimplification. The process that Sorbet uses to type check code is called the pipeline. The pipeline consists of a series of steps that transform code in various ways until it is possible for Sorbet to infer type information and report any errors to the user. Parsing is actually just the very first step of that pipeline. The pipeline looks simple enough on this nice graphic that I made for this talk, but keep in mind that each of these little squares represents a few thousand lines of complex C++ code that were written over the course of years by people who were not me and my teammates. The goal here is not to understand everything that Sorbet does, because I don't know if anybody actually does. Our goal in this project was just to replace this part of the pipeline without accidentally disrupting anything else that's happening later on. Now, you might say, actually, that seems simple enough. Just remove the Sorbet parser, and pop Prism in, and then you're done. After all, these two parsers both convert Ruby code into a parse tree. And we're good. And yeah, like that is technically true. However, there is no rule that all Ruby parsers must create the exact same parse tree. Two parsers can represent Ruby code in totally different ways. And so while the trees created by the Sorbet parser and Prism might be similar in a lot of cases, there will also be differences in structure. So let's look at some examples. At the top, we have a Ruby program. In this case, just the keyword true. Then we have the parse trees created by the Sorbet parser and Prism representing that program. So this is the absolute simplest example. In this example, the parse trees generated by Prism and Sorbet are going to be pretty much identical. The nodes have slightly different names, but structurally, they're the same. Now, let's look at a slightly more complicated example. Here we have two parse trees representing our say hello method, or a call to our say hello method. So we're already familiar with Sorbet's parse tree, which we saw earlier in the talk. There's a send node, and it has one argument, which is a string node with the value world. However, when we look at the Prism tree, we'll see the structure of the two parse trees differ a little bit. We'll see that the Prism parse tree represents the call to this method as a call node, so a slightly different name. And then it references an arguments node, which Sorbet does not have. And then that arguments node has a reference to the string node with the value world. So the trees are no longer structurally the same. However, the difference here isn't too large. If this was the only change, it would be really easy to account for. So now, let's imagine we have a different method called method with block. Very creative. And this method takes a block argument. We're going to see the structure of the trees get a little weird. So if we look at the parse tree generated by Prism first, well, we have a call node representing the method call. And then that call node references a block node, which stores the body of the block in a statements node. And then finally, it has a node for the yield keyword. This structure is very linear, and so I think it makes quite a bit of sense. However, if we look at the Sorbet parse tree on the left, we'll see the block node is the topmost node of the tree structure. And this node has references to both the send node and to the yield, the node representing the yield keyword. So despite the fact that these two parse trees represent the same code, they are structured totally differently. So if we just tried replacing the Sorbet parser with Prism, we would have to rewrite the next stage of the pipeline, called the desugarer, to account for the differences between those two parse trees. This assumes, of course, that we know all the differences, which we don't, because they are not documented anywhere. Of course, this approach runs the risk of propagating changes across the whole pipeline, and then forcing us to spend the entire project chasing down bugs resulting from small differences in the Prism and Sorbet AST's parse trees that are breaking something somewhere along the way. So this might be doable, but we thought there has to be a better approach. This is when we came up with the idea of adding a translation layer. In this approach, we create a little detour in the Sorbet pipeline. First, we parse the code with Prism. Then, instead of immediately going to the desugar step, we'll translate from Prism's AST or Prism's parse tree to Sorbet's parse tree, hence the name translation layer. Once our code is structured as though it had gone through the Sorbet parser, then the rest of the Sorbet pipeline can continue as normal. Now, I'm going to show you what the translation layer looks like in practice. There are only 2 days until Halloween, and I don't want to scare you too much, but the following slides contain some C++ code. If you're used to writing Ruby, you may want to avert your gaze. I'm just kidding. But I'll walk you through line by line and make sure that I don't leave anyone with any nightmares. So the translation layer is largely comprised of a function called, you guessed it, translate. The translate function takes as an argument a PM node T object. This is Prism's representation of a node. Then it returns a unique pointer to a parser node object, which is Sorbet's representation of a node. So this method definition makes a lot of sense. We have a function that takes a Prism node and then translates it to a Sorbet node and returns that node. Inside this function, we're going to have a giant switch statement. This is the C++ version of a Ruby case. The switch statement is going to check the PM node type of the Prism node. This just means it's going to check what kind of node has been passed to the function from a list of all of the potential types of Prism nodes. Inside the switch statement, we're going to have a case for every possible node type in Prism. And inside those cases, we're going to do two things. First, we're going to do the translation between the Prism node and its corresponding node or nodes in the Sorbet parse tree. And then, if this node has a reference to any children, we're going to translate those children by recursing back into our translate function and starting the process all over again. This will be repeated for every single node type until we have handled all of the Prism node types and translated them into the corresponding Sorbet parse tree structure. Now, there are approximately 145 node types, and we actually just merged translations for the last one yesterday. So this work is literally happening as we speak. Now, we chose to pursue the translation layer approach because there are some pretty obvious benefits. First, writing a translation between the Sorbet and Prism parse trees would basically save us from changing any of the existing code in the Sorbet pipeline, at least not right now. It would allow us to add the smallest amount of code possible in order to keep working towards our goal. Second, writing a translation layer between these two parse trees would allow us to essentially document all the differences between them. Then, if we ever wanted to remove the translation layer and skip directly from Prism to that desugar step in the Sorbet pipeline, we could use the knowledge we gain by writing the translation layer to proceed with more confidence. Of course, any plan is also going to have some drawbacks. And the most obvious one for the translation layer is that it would be adding code to Sorbet instead of replacing existing code. So this could potentially slow Sorbet down or cause it to use more memory. However, we didn't know either of these things for sure. When examining the trade-offs, the benefits seemed to outweigh the risks. And luckily, we had an approach to make sure our implementation was meeting the performance and memory standards of Sorbet. So at the beginning of this project, we set a few concrete goals to make sure we weren't harming Sorbet's performance. First, we wanted to make sure that we didn't slow Sorbet down significantly, because it's important that Sorbet can type check quickly, even on large applications like Shopify's Ruby monolith. We also didn't want to use significantly more memory than Sorbet does right now, because once again, that would impact Sorbet's ability to type check large Ruby applications. It was important to define these goals going into the project because we could use them to measure our success as we went along and help us make decisions and prioritize the work we wanted to do. So let's talk about how we're measuring performance. Generally, to assess the performance of your program, you're going to want to benchmark it. This means you're going to compare your code's performance to some other standard and see how they match up. The way benchmarking works is generally you choose a certain time interval, say 3 seconds, and then compare how many times you can run your two programs in that amount of time. So in our case, we're benchmarking against the existing Sorbet parser. So we'll first parse a piece of code with the Sorbet parser as many times as possible in 3 seconds. Then we'll parse the same piece of code with Prism as many times as possible in 3 seconds and compare those amount of times. So these are the results from our most recent run of the benchmarks. When we compare just the two parsers without the translation layer, we found that Prism is about 1.4 times as fast as the Sorbet parser, which is a really excellent result considering Sorbet is already so highly optimized. Then, when we compared the entire type checking pipeline, including the translation layer, we found that Sorbet with Prism performed just as well as Sorbet without it. This is also promising because it means that even with extra code added to the pipeline, we are not harming Sorbet's performance. So our second goal going into the project was not to degrade the memory use of the Sorbet pipeline. Our current approach to comparing memory usage is a little bit simpler than performance, I think. We use a command line tool called gtime to sample the memory usage when parsing with the Sorbet parser versus Prism. Then we compare the peak memory of the two runs to see which parser is more memory intensive. When we did this comparison for the Sorbet and Prism parsers with no translation layer, we found that at their respective peaks, Prism used about 2/3 as much memory as the current Sorbet parser, which once again is an excellent result considering Sorbet is already optimized to use as little memory as possible. Then, even when we ran the entire Sorbet pipeline with the translation layer, the peak memory usage with Prism and without ended up being about the same. So in the long run, even adding more code did not have an impact on the memory usage of Sorbet. So if we revisit our two goals for this project, it looks like we're on track to hit both of them. Checking this early and often in the project has given us confidence in our approach and helped us prioritize the most important work. In this case, we haven't prioritized performance improvement work because we know that even with our translation layer, using Prism and Sorbet is just as performant as the existing Sorbet parser and uses about as much memory. So now we've done the bulk of the implementation in this project, and we've made sure that we're going to meet our performance goals. What do we have left to do? A huge part of Sorbet's functionality is obviously detecting and correcting type checking errors, as we saw at the beginning of this talk. So for this project to be successful, we need to make sure that during the parsing stage in Sorbet, we continue to detect any parsing related errors, report them to the user, and offer the right corrections. So we have to do some work to make sure we're still doing that. Next, we need to collaborate with the Sorbet team at Stripe to get our code into a state where they feel great about adding it back to the original Sorbet project, which is also known as upstreaming. And finally, once Shopify is using Sorbet with Prism, then we can think about removing the translation layer. As I mentioned earlier, Sorbet is performing great with Prism, even with the existence of the translation layer. So we don't necessarily have to rush to get it removed. However, once we do remove it, we should see performance improvements in Sorbet, and we will be able to remove the old Sorbet parser once and for all, making the Sorbet architecture simpler and easier to maintain. We're nearing the end of this talk, and you might still be wondering, how is this relevant to me? And I have some thoughts on this subject. So this talk was written to share our work replacing Sorbet's parser with Prism. However, I think that's just a specific example of making a big change to a complex system. And as software developers, we do this all the time. Imagine that you're working at a company that currently stores some data as XML, and they want to switch to using JSON instead. You're going to have to write some code that allows you to do that switch without interrupting any other parts of your data flow pipeline. That's not that different from this project. Or maybe you want to introduce service objects into your architecture. Also not very different. Whatever the case may be, I think we can take some lessons from this talk and apply them to whatever project you might be working on next. So our first lesson is that complexity can exist at a community level. Remember that all of the existing Ruby parsers that came before Prism were perfectly functional. The issue was that they were never meant to be shared between projects. It's easy to forget that when we write software, we are writing it in a global ecosystem of people who are often trying to accomplish the same things. By implementing our own solutions that can't be reused, we can create unnecessary complexity and toil, not just for ourselves or our teammates, but developers across the community. So if we instead collectively invest in making a shared solution really great, then we can all reap the rewards. Our next lesson was that to make a big change to a complex system, we had to make the change as small as possible. There is an oft-quoted saying by Kent Beck, "First make the hard change easy, then make the easy change." I don't think working in Sorbet will ever be easy, but we managed to reduce the scope and complexity of the project by changing as little as possible, at least for now. When considering the trade-offs between different approaches to your next project, consider which approach will allow you to see results with as little impact as possible to existing code. Finally, we learned about setting specific success criteria for our projects and then testing them to make sure we are on the right track. This project isn't quite done yet, and when it is done, ideally users of Sorbet should not even notice a difference. However, I'll note that this project had an impact on Sorbet, on the state of parsing in the Ruby community, and on me through all the lessons I learned. After listening to this talk, I hope you'll continue to think of software as something that is written by and for community. I hope you'll tackle big projects with small changes, and I hope you'll be specific about your goals to help you reach success. Thank you.